This is another video on sensitivity analysis in linear programming. And in the previous episodes, I showed you what happens when we change objective coefficients. For example, in this model that you see here on the right, where we maximize profit subject to certain constraints and non-negativities, where we're trying to decide how many units of two products to produce, we were considering in the previous videos what happens to the coefficients, to the optimal solution and profits when the coefficients of the objective, 350 and 300, are changed to other numbers. Now, in this episode and a few subsequent episodes, I'm going to show you what happens when you change the right-hand sides, the right-hand side values of constraints. So in this case, all resources are actually, all constraints are actually resource constraints, meaning that they are limits on some resources that we are using when we schedule activities like production. Right, so here the first constraint says the total number of pumps that we use, and every product uses one pump, the total number cannot exceed 200. And the total number of labor hours that we schedule our workers to work for cannot exceed a given number. And the same thing, we have some available feet of tubing. Again, we do not want to exceed the upper limit. So the left-hand side of these constraints is always the number of used units of resource, and the right-hand side is always the number of available resources, and the constraints are all less than or equal. The optimal solution of this problem is to produce 122 aquaspas and 78 hydroluxes, and the optimal profit achieved at this solution is $66,100. And here you see the sensitivity reports, the parts of sensitivity reports from Excel and from Python when we use Gurobi solver, right? This is the line in Python that you can use to generate this, that deal with sensitivity to changes in the constraints, in particular in the right-hand side values. So what we see here, let's look first at Excel. It's just a list of constraints, the big constraints, the three resource constraints. The lower bound values on the variables are not included in this list. And for each we see final value is just the value of the left-hand side calculated when we plug in the optimal solution in it. So for example, here we're using all the pumps. The right-hand side is shown here, right? So the right-hand side is 200. And then when you produce 122 and 78, you can actually calculate that the left-hand side value at this solution is 122 plus 78, which means it's also 200. And here you see it displayed here in the first column on the Excel sensitivity report. And then the same happens for the labor hours. The same number is used as available, but for the feet of tubing, the number that is used is 2,712 when 2,800 are available, right? So this constraint, we will say, has a certain slack. Okay, and then what do we have? What else do we have? We have something called shadow price in the second column. So the shadow price is a certain price of resource that we will consider later on. And we also have, after the right-hand side, we have allowable increase and allowable decrease values that will define a certain range for those right-hand side values that we see here. And a similar information is displayed in Python, information obtained from Gurobi solver. So in addition, you see I printed here something called sense. Sense basically defines whether the constraint is equality or less than or equal or greater than or equal. Actually, sense less means that the constraints are actually less than or equal. Equality is always there. We're also given slack, and you notice that slack is actually carrying the same information as the value the difference between the right-hand side and the final value in Excel, right? So what we can see here is that this slack 168 is actually the difference between the constraint right-hand side and the final value, right? The final value of the constraint. So the right-hand side value minus left-hand side value, which is the value of this constraint. let's say we're considering constraint number 3, the value of this constraint at the optimal solution. When you plug in the optimal solution, you get this 2,712. So the difference between those two, right, is 2,880 minus 2,712 is actually equal to 168, and that's what we call slack. So this is a formula that is used to calculate slack, right? And you will see this formula here, right-hand side minus final value or left-hand side value is the definition of the slack. So clean up here a little bit. So the slack basically can be actually calculated from the final value around the right-hand side value. So what is the information that we see actually in both of those tables? So the first thing you already said is the slack, right, given here directly or as a difference in columns 3 and 1 in the Excel report. And this is basically denoting something that for resource constraint will mean unused units of resource, right? When the constraint is less than or equal, it will tell us is the constraint satisfied with equality or is the left-hand side smaller than the right-hand side. In this case, for the first two constraints, they are satisfied with equality. It's 0 slack here and 0 slack here, but the last constraint actually has a positive slack, and that means not all feet of tubing that were available have been used. Okay, what else do we have? We have this shadow price. So in Excel, it's called shadow price. In Gurobi, it's actually called pi, and also called dual value, right? What this means is it's a marginal value of resource. So it actually means how valuable each of those resources, pumps, labor hours, and feet of tubing, are as measured in terms of increase in profit. Right? So it's something like an extra pump would be worth how much in terms of contributing to the profit? Well, it would be worth $200 if I had an extra pump. If I had an extra labor hour, it would be worth $16.67. And if I had an extra foot of tubing, it would be worth 0. It wouldn't increase the profit. Right? So it's important to notice that actually the unit of the shadow price is like unit of objective divided by the unit of the constraint. In this case, for example, the first shadow price, this 200 should be measured as dollars of profit divided by number of pumps, right? So dollars per pump. This would be dollars per labor hour, and this would be dollars per foot of tubing, right? So shadow price, we will see how we can use it to actually determine the impact of changing available resources on the optimal objective function value, on this optimal profit that we achieve here. And the third thing we're given is actually in the last 3 columns, it's what we call range of feasibility. And you will see by analogy to range of optimality that we saw for the objective coefficients, range of feasibility is defined again in Excel, is defined as using allowable increase and decrease. And so basically it says, what's the range with respect to the current right-hand side? So you take the right-hand side, subtract allowable decrease, that's the lower limit of the range, and right-hand side plus allowable increase gives you the upper limit. And again, these limits are given directly as in the range of optimality. For range of feasibility, they're given directly. So for example, what you see here, the range of feasibility is from 174 to 207. Of course, it includes the 200, right? And this 174 is in fact, if you look at the Excel report, it's 200 minus allowable decrease 26, right? And then the 207 is 200 plus allowable increase 7. That's 207, right? And the range of feasibility is basically, you can think about it as a range in which the shadow price works. So the shadow price that you see defined earlier, we will be able to use it to determine the impact on the profit as long as we're within the changes of right-hand side within range of feasibility, right? So basically what we can learn from this, and this is a definition, a kind of definition, if one right-hand side value changes within the range of feasibility that's defined above, and all other coefficients in the model remain the same, then we will know that the optimal objective function value will increase by shadow price times the increase in the right-hand side, right? So, and then decrease if we have a decrease of right-hand side. So basically, that's how we will apply the shadow price as a marginal value of resources to determine the change in the profit, the objective function value, when we change one of the right-hand sides. And again, so this is, I hope you see, a very analogous rule to what we had for the objective coefficients. However, there's a big difference. When we were changing objective coefficients, we said optimal solution will not change. However, in this case, when we are within the range, we say optimal objective function value will change according to the shadow price. So there is a very different conclusion when you are within the range, right? In the objective coefficients, we said when you change the objective coefficient, we know something about the optimal solution. And here, when we change the right-hand sides, we know something about the optimal value of the objective function, not the solution, right? This doesn't say anything about the solution. And then there is one more thing. There is something called 100% rule, but this time for right-hand side values, right? If you change more than one right-hand side value, right, and all other coefficients in the model remain the same, the change in the optimal objective function value can be calculated using shadow prices if the total percentage of the allowable changes of those right-hand sides do not exceed 100%, right, when expressed relatively percentage, and added all of them, right? So I'll leave the 100% rule for later. For now, we want to consider this. So what kind of questions can we answer using those using the shadow prices and ranges of feasibility. But before we go there, I want to consider one more thing. Every constraint in the model that we see can be either a binding constraint or a non-binding constraint. So let us define what a binding constraint is. Well, we will say that the constraint is binding when it was the reason why we could not improve the optimal objective function value, right? So for example, why did we achieve $66,100 of profit? Why didn't we get a higher profit? Well, it was because there were certain constraints that didn't allow us to improve this profit further, right? If you recall, and I have these videos about the graphical method, right? There are some constraints that will stop the improvement of the objective function, and these are called the binding constraints. And there are some constraints that are, even though they are limiting the region, they are creating boundaries of the feasible region, they might happen not to be binding, they might be kind of not active in the optimal solution. So how can we detect if a constraint is binding? So actually you can obtain this information often from the solver. Excel has this in the answer report, but we can also conclude from the information that we have here. So for example, if a shadow price is not zero, the corresponding constraint is always binding, right? So we see shadow price here, right, or from this report, first and second constraint have positive shadow prices. Even if they were negative, it would be the same. If it's non-zero, then the constraint must be binding. So we know the first two constraints, the pumps and the labor, are actually binding constraints, right? They are the constraints that stopped the improvement of the profit. Another consideration, if slack is not equal to zero, then the corresponding constraint must be non-binding. Right? So for example, here we have a constraint with slack 168, and what that means is that this tubing constraint, the third constraint, is actually non-binding. So that means this constraint definitely is not preventing improving of the optimal objective function value, right? It's actually possible that we have both shadow price and slack equal to zero. It doesn't happen very often, but it can. And in that case, the constraint might be binding or non-binding. This information actually cannot be concluded from the sensitivity report here, but you can also find out, ask the solver about this information or get it from some reports and find out which constraint solver considered as binding. And notice we can never have shadow price non-zero and slack at the same time non-zero, because that would mean resource is not used, but it is actually valuable for improving the objective. So it would be a contradiction, right? Okay, so the questions that you can answer using the sensitivity report, the second part of the sensitivity report relating to constraints, here is the first question. Okay, the first question, what if only 195 pumps are available instead of 200, right? So we basically look at the first constraint. We say, well, we assumed 200 pumps are available, but what if we're wrong? What if only 195 are available, or the right-hand side of this constraint is decreased by 5? So how can we analyze this information, again, using sensitivity report? So if you recall what I said about objective coefficients, the same here applies. We could basically plug in 195 into the right-hand side, update our Excel or Gurobi Python model, and just resolve and see what happens, right? But obviously, we could ask a lot of questions like this and generate a lot of slightly different models with slightly different data, actually, and solve them. And we would have a lot of cases, and we wouldn't learn much because there would be just too many examples. But here we have some meta information, right, in very concise information in the format of sensitivity report, and we can answer many questions like this just from this data, right? So first thing to recognize is that 195 is within the range of feasibility, right? The range of feasibility, which is here, right? This is the right-hand side, and we're changing it to 195, but we're still within the range of feasibility, which is from 174 to 207. All right, so we are within the range of feasibility, or we could say, right, we could say that alternatively, we could say a decrease by 5 is smaller than or equal to allowable decrease, which is given here in Excel, and the last column at the top, which is equal to 26, right? So if we know this, so what can we conclude from this? Now, remember, when we were changing the objective coefficients, we said, so the optimal solution doesn't change. Here, the conclusion is different. When we're changing at the right-hand side, we're saying, so the change in the optimal objective function value can be determined using the shadow price, right? And the shadow price for this constraint, right, is here. Shadow price, pi, is 200. And let us actually put a unit here. 200 of what? It's $200 per pump. Why is it dollars per pump? Because the objective is profit in dollars, and the constraint is measured as the number of pumps. 200 means number of pumps, and we're decreasing the 200 pumps to 195 pumps, right? So this is a bit of a coincidence that the shadow price is the same as the right-hand side, right? These two numbers are the same, but of course they mean something very different. This means number of pumps, and this means dollars of profit that we can gain from an extra pump, right? Or lose also, right? So this is the first thing. So we know we can use the shadow price. So we can, since we can determine the optimal objective function value, let's just determine it, right? So we can say, right, the optimal objective function value will, right, we decrease the right-hand side, so we're also going to decrease, right, it will decrease by, and then we decrease the right-hand side by 5, so it will be 5 times the shadow price, right? For 5 pumps less, we get 5 times the shadow price less of profit, right? So this will be 5 times 200. Remember, this is 5 pumps, if you like, pumps, divided, multiplied by $200 per pump. So basically the pumps disappear from this, right? Multiplied and divided by pump, it becomes 5 times 200 and just dollars. So this is $1,000, right? So the optimal objective function value will decrease by 1,000. So, right, it will become, or will be 65,100, right? So it will decrease. Now, we can also ask ourselves, right? So we know the shadow price can be used and it determines the value of the optimal objective function, optimal objective function value, but it doesn't tell us anything about the solution. But we can also conclude what happens to the solution in terms of whether it changes or not, right? And there are two ways of thinking about this, at least, given that we restricted a binding constraint, right? Remember, this constraint has a shadow price that's not zero. So it's a binding constraint. It's like a zero, right? It's a binding constraint. This is the one that prevented improvement of the solution. So we're now restricting this constraint, right? And actually, in fact, we're sure the old optimal solution will not even be feasible. If you recall, right, this solution used 200 pumps. X1 plus X2, if you add these two, is 200. And now we no longer have 200, we have 195. So when you restrict a binding constraint, right, you can say the optimal solution will no longer be feasible. So the optimal solution will certainly change, right? And there's another way of thinking about this. So this is also kind of the same conclusion using a different fact. Given that optimal objective function value changed, right? Changed, and the optimal solution must also be changing, right? And why is that? Because you see, what's the optimal, right? What's the 65,100? It's the value of the objective function, right? It's the value of 350 x1 and 300 x2. So if it was before 66,000 and it is now 65,000, right? Then how can it be the same solution? If I plug in the same 122 and 78 in this objective, I will obviously get 66,100. So if I know the optimal solution the optimal objective function value will change to 65,100, it must be through the change of the optimal solution. So one thing to notice here is that the shadow price kind of gives us an information that is about the optimal objective function value change. However, this change is actually achieved through the change in the solution, right? So to remember, what we need to remember about what's happening here is this, that remember when we had the graphical method and we had some binding constraint, we had the pumps constraint, right? This was the pumps, and then this was labor, and then the optimal solution was actually somewhere here, right, in this point, and then these are actually the binding constraints, right? So I'll just put a small symbol B, binding, right? And there was also another constraint, tubing, somewhere here, and this was a non-binding constraint, So when we're changing the right-hand side of the pumps, we're in fact moving this line is no longer here, it's going to be somewhere here, it will shift, and therefore this solution is no longer optimal, and in fact it will move somewhere, the same constraints will be binding, so the solution will be somewhere here, and this is why we will lose a $1,000 of profit, right? So the thing to remember here is that when you change the shadow price, when you change the right-hand side, right? So when you change the right-hand side change actually causes solution change, right? The solution, optimal solution changes, right? And that change changes the profit, right? Profit change actually, or in general, optimal objective function change, right? And notice that the shadow price is actually what's giving us somehow a shortcut, right? Shadow price tells me how the profit will change without telling me how the optimal solution will change. But the optimal solution, I can determine whether it will change or not. If the profit changes, it must be that the optimal solution has changed, right? Or another way, if we know that we just changed something in the binding constraints, we must also be changing the optimal solution, because the binding constraints are what determines the optimal solution. Here is another question. What if I have 100 additional labor hours available, right? So this question is asking about the labor constraint and saying, well, I had now, let's say, per week, 1,566 labor hours available, number of workers who can all work in a given week. And now I'm saying I will have extra 100 labor hours available. Maybe I have extra workers, maybe some of them can work longer, right? Whatever the reason. Well, again, this is one of the many possible changes. Can I conclude something from the sensitivity report about this? Yes, I can. So as before, the first thing is an increase by 100, right? Of the right-hand side, that was 1566. That's the result will be 1666 labor hours. And this is, again, within the range of feasibility right? The range of feasibility, which is given here, from 1440 to 1,800, right? So we are still within the range. We increased, but we're still in the range, right? And alternatively, I could say increase by 100 is less than or equal the allowable increase, which is given in here in the solver for labor hours. It's 234, right? So again, what do I conclude from this? So the change in the optimal objective function value can be determined using the shadow price. And the shadow price, now that we're concerned, this is constraint number 2, right? Remember, we're considering now the right-hand side of constraint number 2. So we have to look at the shadow price for constraint number 2, which is 16.67. And again, let's put a unit here to be clear what we're doing. This is how much dollars of profit we will gain or lose when we change the available hours of labor. So let's just call it dollars per hour. But remember, this is dollars of profit by labor per labor hour. So we can determine, so what will be the change? The optimal objective function value will, right, again, right-hand side was increased by 100. The optimal objective function value will increase by 100 times the shadow price, right? Notice, if the shadow price were negative, and this happens in other problems, not this one and this one, all shadow prices have to be positive or zero because they are all resources and we're maximizing profit. But if the shadow price was negative, I would still say it will increase by 100 times shadow price. And then if the shadow price is negative, I would say, oh, increasing by a negative number actually means decreasing, right? So then it would, in fact, be a decrease. But here, of course, it is going to be an increase because it's 100 times 16.7, so 16.67, so it's actually $167, right? So the increase is by this much. So the as a result, right, it will be, right, we need to subtract. When we subtract it, we will find out it's 64,433, right? Again, as before, we can ask ourselves, okay, what happens then to the optimal solution? Well, given that we relax binding constraint, right? Remember, graphically, we're going to expand the feasible region, so we'll have more feasible points, right? And if this was a binding constraint, the optimal solution, actually, to be certain, instead of saying will change, I might say might change, because it is possible, it could be possible that when you relax a binding constraint, you might have another constraint that happens to be binding in the same point, right? So it could be that another binding constraint will prevent further improvement, right? So, but also we know that the old optimal solution remains feasible, right? Why is it feasible? It is feasible because, remember, before, when this was a binding constraint, we were using actually all the, right? The slack was 0. We were using all the labor hours, and now we have 100 labor hours more, but still, we can still use the 1566, and we could still achieve this profit. Oh, sorry, this should have been an increase, not decrease. So it should have been 767. It's not a decrease, it's an increase, right? So it's 66,100 plus 1667, that's 67,767, right? So we relax the binding constraint, the optimal solution might change. It most likely will change, but we can be sure it actually changes because the other fact, given that the optimal objective function value changes, the optimal solution must be changing too, right? Why? Because if the value of this function just increased and we have not changed 350 or 300, those coefficients, then something must be changing in the x1 or x2 or both of them, right? In many cases, in fact, both of those variables will change, but one of them might increase, another might decrease. And if you have a solution consisting of much more values, like much more variables in the model, then some variables might change more than one. Some of them increase, some of them decrease, and the net effect is this increase, in this case, in the optimal objective function value. So here were the two examples of changing the right-hand sides when we have when we're staying within the allowable increase or decrease, or within the range of feasibility. I want to show you one more example when the shadow price is 0. So we're going to consider the third constraint now. What if additional 1,000 feet of tubing are available, right? So consider this. The last constraint, remember, we determined it's not binding because it has a slack that is positive, right? This is, in this case, the number of unused units of resource. We had 168 feet of tubing that were not used, right? So what if we now add more feet of tubing available, right? So instead of 2,800, we will now have 3,880 feet of tubing. And so, again, as before, we can say this is within the range of feasibility. But what is this range of feasibility? Well, a range of feasibility is from this to this. What is, right? So the lower limit is 2,712, but what is the upper limit? Well, the solver says 1e plus 100, but that's like 1 with 100 zeros, right? And what that effectively the solver is trying to tell us is that this is plus infinity, right? There's no way to express infinity, but the solver can put a very large number to indicate the same thing. So what this means basically that this is we can increase up to infinity, and the solution, the optimal, not optimal, the shadow price can be used within this range up to the right-hand side, increasing all the way to infinity, so without any limit. And alternatively, we can say that increase by 1,000 is less than or equal than allowable increase, which is shown here in the last line, right? And this allowable increase in Excel is shown as 1 e plus 30. But again, this is a very large number. This is like 1 followed by 30 zeros. So a very large number. And again, the solver is trying to tell us, Excel solver in this case, is trying to tell us that this is plus infinity, right? So anything is smaller than plus infinity, right? So again, as before, the change in the objective function value can be determined using shadow price. And the shadow price now, shadow price for constraint number 3 is 0, right? So 0, and again, let's put a unit just for consistency. It's dollars per foot of tubing, right? The constraint is in feet of tubing and the profit is in dollars. So it's the dollars of profit for every foot of tubing. So that actually tells us we will not gain anything, right? So we could say again, the optimal objective function value will increase by, right, this 1,000, the increase in the right-hand side, times the shadow price, right? But that's now 1,000 times 0, so the increase is by $0. So it will actually not change, right? The optimal objective function value will still be, it will still be 66,100, right? So again, what can we say, what can we say about the solution change, optimal solution, right? Well, the optimal solution will not change because we relaxed a non-binding constraint, right? We relaxed a non-binding constraint which had a slack of 168 feet of tubing, right? After the increase of the right-hand side, right, the slack will be 1,168, right? The additional 1,000 feet of tubing, right? So all we did is we increased the slack. It was not binding, and we just relaxed it, meaning that we allow more feasible solutions, but no new feasible solution is actually better than the one that we determined as optimal before, right? In fact, any increase of the right-hand side, if we were to increase this right-hand side 2,880 here by any number, right, it's not going to change the optimal objective function value or optimal solution, right? And in fact, we could also decrease it, but no more than to this value, right, which is decreased by 168, right? Because if we use up all the slack, this constraint will stop being non-binding, it will actually become binding. So you can see that in this example, when shadow price is 0, allowable decrease in this case is actually equal to the slack, right? It is actually showing the same information. So these were examples of using shadow prices when we change right-hand sides within the range of feasibility. And we were changing one coefficient. And the following videos, I will show you how what happens when you change the right-hand side, but you go outside of the range of feasibility. And then I'll also try to show you what happens when you change multiple right-hand side, not just one.